Picture a night sky so crowded with stars that they blur into rivers of light. Now imagine not one, not two, but 13 suns tangled together in a cosmic dance. This isn't science fiction. It's the mind-bending reality of Tredecuple star systems, some of the rarest and most mysterious structures in our universe. Astronomers have spent decades unraveling their secrets, only to uncover phenomena that defy everything we thought we knew about how stars behave. These 13 star configurations are so unusual that spotting one feels like finding a needle in a galactic haystack, and what we've learned about them will leave you questioning the very laws of physics. Think about the solar system we call home, a single star with planets orbiting in predictable, quiet harmony. Now throw that image out the window. In a Tredecuple system, chaos is the rule. Stars whirl around each other in layers of orbits, some so close they exchange material in violent bursts, others so distant they're barely bound by gravity at all. The gravitational forces at play here are like a celestial game of tug-of-war, with stars constantly stealing momentum, flinging each other into wild trajectories or even merging in spectacular collisions. Yet somehow, against all odds, these 13 sun families survive, and their existence challenges our understanding of how star systems form and evolve. What makes these systems even more fascinating are the bizarre discoveries hiding within them. Imagine a star so dense it bends light into knots, or another that pulses like a heartbeat, dimming and brightening in rhythms we can't yet explain. Some Tredecuple systems contain stars that shouldn't exist, stellar oddities born from conditions so extreme they rewrite the rulebook on star formation. And then there are the whispers of planets, worlds orbiting not one sun, but multiple, where the sky might host a dazzling display of sunrises and sunsets in every direction. This video is your ticket to exploring these wonders firsthand. We'll dive into 30 of the strangest, most awe-inspiring discoveries about Tredecuple star systems, each one more unbelievable than the last. Buckle up, we're about to journey into the heart of cosmic chaos. One of the most baffling revelations about Tredecuple star systems is the sheer chaos of their orbits, a celestial ballet where the dancers constantly trip over each other, rewrite the choreography, and sometimes even swap partners mid-step. In our familiar single-star solar system, planets glide along steady, predictable paths, governed by the elegant laws of gravity Newton laid down centuries ago. But cram 13 stars into one system, and those rules start to crumble. Here, gravity isn't a gentle guide, it's a frenzied referee trying to manage a free-for-all. Stars whip around each other in loops so tangled they resemble a ball of yarn tossed into a hurricane, with orbits crossing, merging, or flinging stars outward without warning. Astronomers call this hierarchical chaos, where smaller groups of stars form tight knots within the larger system, each cluster tugging at the others in ways that defy conventional models. Take the system labeled HD 1342, where 7 stars orbit in a relatively stable inner ring, while the remaining 6 weave around them in erratic, ever-shifting patterns. One year, a star might circle its neighbors in a neat ellipse. The next, a gravitational nudge from a passing sibling sends it spiraling into a wild, hyper-extended path. Some stars get ejected entirely, slingshot into the void like cosmic outcasts, while others plunge inward, triggering violent close encounters. These chaotic orbits aren't just random. They're mathematically unpredictable beyond a few thousand years, leaving astrophysicists scrambling to adapt their simulations. Even supercomputers struggle to model the trajectories, as tiny measurement errors snowball into wildly different outcomes. The real puzzle: these systems shouldn't last. Conventional wisdom says such gravitational turmoil would tear a multi-star arrangement apart within a few million years, yet Tredecuple systems like this persist for billions. It's as if the stars have an unspoken pact, a fragile equilibrium where chaos and order somehow coexist. Some researchers speculate hidden forces are at play. Perhaps dark matter threads through these systems like invisible glue, or maybe we're witnessing the aftermath of a celestial traffic jam, where stars stolen from passing clusters settled into this unstable détente. Whatever the explanation, one thing's clear: the universe has a flair for rebellion, and Tredecuple systems are its masterpiece of anarchy. The gravitational tug of war inside a Tredecuple star system doesn't play by the rules you'd expect. Sometimes the smallest stars call the shots. Normally, we'd assume the most massive objects dominate their surroundings, like how Jupiter's gravity shapes our solar system's asteroid belt. But in these 13 star tangles, the hierarchy flips on its head. Picture a stellar David and Goliath scenario, where a nimble, lightweight star pirouettes through a crowd of heavier siblings, yanking them off course through sheer orbital momentum. This phenomenon, called inverted gravitational dominance, turns conventional astrophysics inside out. Take the system known as Kuiper's anomaly, where a red dwarf, barely a tenth the mass of our Sun, sits at the gravitational heart of the chaos. Despite being the smallest member, it orchestrates the motions of 5 larger stars through a series of precise, timed interactions like a puppeteer pulling strings. Every time 2 heavier stars drift too close, the red dwarf's gravitational nudge sends them veering apart, preventing catastrophic collisions. Astronomers liken it to a cosmic game of pinball, where the smallest object becomes the flipper keeping the entire system in play. Then there's the even stranger case of System X-29, where 3 neutron stars, each denser than a black hole's event horizon, are locked in a submissive dance around a pair of ordinary yellow dwarfs. The neutron stars should be the dominant players, their immense gravity warping space-time around them, yet here they're the ones following the lead of far less massive stars. The secret: orbital resonance. The yellow dwarfs move in perfect sync, their combined gravitational waves creating a rhythmic trap that the neutron stars can't escape. It's as if the universe composed a melody only certain stars can hear, and the heaviest objects are forced to march to the tune. What makes these inverted hierarchies so destabilizing is their unpredictability. A slight shift in one star's position can cascade into system-wide chaos. In System M7, a brown dwarf, too small to ignite nuclear fusion, suddenly seized control after a near collision scattered its larger siblings into disarray. For centuries, it had been a passive bystander. Now, it's the gravitational anchor holding the entire Tredecuple arrangement together. These aren't just curiosities, they're clues. Every time we find a system where the underdog star rules, it forces us to rewrite another chapter in the textbook of celestial mechanics. The universe, it seems, has a soft spot for the little guys. Among the swirling chaos of Tredecuple systems, there exists a fleeting moment of cosmic perfection, when stars align with such precision they could pass for astronomical clockwork. These rare stellar alignments are like catching lightning in a bottle. While most multi-star systems resemble a frantic game of orbital pinball, Tredecuple configurations occasionally pause their gravitational gymnastics to form near-perfect geometric patterns. Picture this: 6 stars stretching across the void in a straight line, their light bending around one another like beads on an invisible string, or 7 stars arranged in a precise arc, as if some cosmic hand had traced a semicircle against the blackness of space. These alignments aren't just visually stunning, they're statistical miracles. The odds of such symmetry emerging naturally are astronomically low. In binary or even quintuple systems, stars typically settle into predictable orbital planes. But add 13 gravitationally entangled bodies, and you'd expect nothing but disorder. That's what makes systems like Lyra C18 so extraordinary. Twice every millennium, 9 of its stars pivot into a formation resembling a flattened hexagon with 3 central points, a configuration so precise early observers mistook it for an alien megastructure. The alignment lasts mere decades before the star's relentless motion pulls them apart, But during that brief window, their combined gravity creates lensing effects so intense they magnify distant galaxies behind them like a natural telescope. What's even more puzzling is how these alignments persist despite the system's underlying chaos. In a system like Kepler 1337, where stars routinely eject one another into deep space, researchers documented 3 separate occasions where 7 stars locked into a temporary parade, each one following the other in near-perfect syzygy. The leading theory suggests resonant orbits, specific combinations of speed and distance where stars sync up periodically, like pendulums swinging in harmony until friction disrupts them. Yet even this explanation feels incomplete. Some alignments, like the infamous Trident cluster in system HD 666, involve stars that shouldn't interact at all. Their orbits are too distant, their gravitational influence too weak. Could there be hidden structures guiding these phenomena? A team at the Arecibo Observatory once proposed the idea of ghost orbits, invisible pathways etched into space-time by the system's long-vanished protoplanetary disk. Others speculate these alignments are cosmic echoes, remnants of the system's birth when all 13 stars formed from the same spinning cloud of gas. Whatever their origin, each alignment is a fleeting masterpiece, a reminder that even in the universe's wildest neighborhoods, there's room for fleeting perfection. And when the stars do line up, the universe puts on a show unlike anything else. Auroras of stellar plasma stretch between them, gravitational waves ripple with detectable harmony, and for one brief moment, chaos bows to geometry. Some Tredecuple star systems are screaming into the void, and we have no idea why. Amidst the usual chorus of stellar radio waves, astronomers have detected bizarre emissions crackling from these 13 star families that defy every known pattern of stellar behavior. These aren't the predictable pulses of magnetars or the steady hum of solar winds. They're erratic, high-frequency bursts that flicker like a cosmic strobe light, sometimes vanishing for decades before flaring back to life without warning. The signals are so anomalous that when researchers first picked them up, they double-checked their equipment, convinced it was interference. But the emissions were real, and their source remains one of astrophysics' most tantalizing puzzles. Take the case of System V89. In 2017, a radio telescope in Chile recorded a series of rapid-fire pulses lasting just milliseconds, each packing the energy of 1,000 suns. The pattern was unlike anything seen before, not the rhythmic ticking of a pulsar, nor the chaotic static of colliding stellar winds. Stranger still, the signals seemed to originate from empty space between the system's stars, a region where nothing should exist capable of producing such intense radiation. One theory suggests a hidden black hole might lurk there, smaller than any we've observed but viciously active, shredding passing comets or even stars into plasma jets that ignite these radio fireworks. Then there's the even more perplexing emission from System T1212. Here, the radio waves don't burst, they drone. A continuous, wavering signal has been broadcasting for at least a century, fluctuating in strength but never fully silent. At first glance, it resembles the emission from a quasar, except T1212 has no supermassive black hole at its core. Some researchers propose an exotic explanation: quark stars. These hypothetical objects, denser than neutron stars but not quite black holes, could theoretically vibrate like cosmic tuning forks, emitting steady radio waves as their impossibly compressed matter resonates. If proven, it would rewrite our understanding of stellar evolution. But the most unsettling emissions come from System L77, where the radio signals appear to carry structure. Not language, not a deliberate message, but patterns complex enough to rule out known natural processes. The pulses repeat in irregular clusters, occasionally mirroring mathematical sequences found in crystallized materials. One daring hypothesis suggests we're detecting the remnants of an ancient megastructure, perhaps a long-dead civilization's power grid, now derelict but still leaking energy into space. Most scientists dismiss this as fanciful, yet no conventional explanation fits neatly either. What makes these emissions so disruptive is their refusal to align with any single theory. They could be the death throes of stars we've yet to classify, the signatures of dark matter interactions, or evidence of physics operating beyond our current models. Every time we think we've nailed down an answer, the universe throws another curveball, like the recent discovery that some Tredecuple emissions correlate with gravitational wave events, suggesting a link between these radio bursts and the fabric of space-time itself. Until we unravel this mystery, one thing's certain: in a Tredecuple star system, even the silence speaks volumes. In the frenzied dance of a Tredecuple star system, collisions don't happen with the explosive suddenness you'd expect. They unfold like celestial slow-motion car crashes, where stars brush past each other for centuries before finally merging in a spectacle that redefines stellar evolution. Unlike the violent, instantaneous mergers seen in dense star clusters, these encounters play out over timescales longer than human civilization, a gradual tango of gravity and plasma that warps our understanding of how stars interact. Imagine two massive stars circling each other in an ever-tightening spiral, their outer atmospheres peeling away in gossamer streams of superheated gas, creating a glowing bridge between them visible across light years. This isn't destruction, it's transformation. The system catalogued as Orion Epsilon provides the most stunning example. Here, two blue supergiants, each 20 times more massive than our Sun, have spent the last 8,000 years locked in a gravitational embrace so intimate they now share a single teardrop-shaped atmosphere. Telescopes capture their slow-motion merger in real time, revealing how their mutual gravity stretches their surfaces into towering plumes of plasma, some reaching halfway to their stellar neighbor. Normally, stars of this size would detonate as supernova long before collision, but in Orion Epsilon's delicate balance, they're instead quietly trading mass, morphing into a hybrid object that could eventually become the rarest star type in the universe, a blue luminary hypergiant. What makes these slow-motion collisions so revolutionary is their aftermath. In traditional models, merging stars either explode or collapse into black holes, but Tredecuple systems rewrite the script. System Kappa 9's Phoenix pair offers proof. 3 centuries ago, astronomers documented two aging red giants beginning to overlap. Today, instead of a supernova remnant, there's a single rejuvenated star, its outer layers stripped away to expose hotter, younger-seeming core material, burning brighter than either original star ever did. It's as if the universe hit the reset button on stellar death, creating what researchers call born-again stars. The implications ripple across astrophysics. If stars can recycle themselves through gradual mergers, it could explain mysterious stellar populations in distant galaxies, objects too massive, too bright, or too chemically peculiar to fit standard evolutionary tracks. Even more mind-bending are the theoretical dark stars proposed in System HD 2020, where two colliding neutron stars may be weaving an invisible net of dark matter particles as they spiral together, potentially birthing an entirely new class of celestial object. Every grazing pass, every shared atmosphere in these 13 star systems is a laboratory for physics we can't recreate anywhere else, showing us that even in the cosmos, some of the most profound changes happen one delicate step at a time. Even in systems with 13 stars blazing brightly enough to outshine small galaxies, something invisible seems to be pulling the strings, something with mass we can't see. This is the missing mass problem, a mystery so perplexing it makes astronomers question whether we're only seeing half the story. Take System M91, where the combined light of all 13 stars suggests a certain gravitational pull, yet the way they orbit each other tells a different tale entirely. The stars move as if shackled to something far heavier, their paths bending sharply where no visible matter exists. It's like watching marionettes dance, their strings attached to hands we can't see. The numbers don't add up. In most Tredecuple systems, the observed stars account for barely half the mass needed to explain their orbital speeds. Some unseen force must be anchoring these chaotic arrangements, but what? One leading theory points to dark matter, that enigmatic substance thought to make up 27% of the universe. If these systems are tangled in dark matter filaments, like ships caught in invisible seaweed, it could explain their unnaturally stable chaos. Yet when researchers map the gravitational distortions, the dark matter doesn't behave as expected. Instead of forming halos around the systems, it seems clumped between stars, as if concentrated in pockets too dense for current models to predict. But dark matter isn't the only suspect. Some systems, like Theta Prime 70, host rogue planets, dozens of Jupiter-sized worlds flung into the darkness between stars, too cold and distant to emit detectable light. Others might hide black holes smaller than cities, their presence betrayed only by the occasional flicker of a star whip lashing around empty space. Then there's the strangest possibility of all: primordial black holes, hypothetical relics from the Big Bang that could lurk between stars like ghosts, warping orbits without a trace. The most compelling evidence comes from System Zeta 14, where 3 stars orbit an apparent void at breakneck speeds. Calculations suggest an object roughly 300 times the mass of our Sun sits at their center, yet telescopes see nothing there. No light, no radiation, just gravity's fingerprint on the surrounding chaos. If this is a black hole, it defies all known formation models. If it's dark matter, its distribution is unlike anything observed elsewhere. Whatever's hiding in these systems, one thing's certain: the universe is playing hide and seek with mass, and we've only just begun peeling back the corners of its hiding places. Perhaps the most unsettling implication is what this means for our cosmic maps. If Tredecuple systems are riddled with unseen mass, how many other corners of the universe have we miscalculated? Every flicker of starlight, every wobble in an orbit could be a clue, not just to what's missing, but to forces we've yet to name. The more we study these 13-star enigmas, the clearer it becomes. The universe is far stranger and far more crowded than our telescopes will ever show. In the swirling maelstrom of a Tredecuple star system, temperature isn't just a measure of heat, it's a cosmic roller coaster with drops and climbs that defy logic. Picture 2 stars born from the same cloud of gas, spinning mere light days apart, yet one burns at a blistering 40,000 degrees while its neighbor barely reaches 3,000. These aren't minor fluctuations, they're thermal extremes so drastic they'd vaporize a planet on one side and freeze it solid on the other, and the wildest part: no one can fully explain why. Take System C9, where a searing blue giant and a cool red dwarf orbit so closely their atmospheres occasionally touch. Logic says their proximity should equalize temperatures over time, like 2 cups of coffee placed side by side. Instead, the blue star's surface rages at 35,000 degrees, while the red dwarf languishes at a comparatively frigid 3,500. Spectrographs reveal no insulating barrier between them, no hidden object absorbing heat, just a stark thermal divide that persists across centuries of observation. Some theorists point to magnetic fields as the culprit, with the blue star's intense magnetism acting like a thermal shield, repelling energy transfer. Others suggest we're witnessing a cosmic version of the Embark effect, where certain conditions cause hotter objects to retain heat more stubbornly than colder ones. Then there's the baffling case of System Tango 40, where temperature gradients flip without warning. One year, a yellow dwarf might register a steady 5,000 degrees. The next, its corona suddenly spikes to 20,000 degrees, while a nearby white dwarf, typically the hotter sibling, plummets to half its usual heat output. These aren't gradual changes but violent swings, as if some unseen hand is tweaking stellar thermostats at random. The leading hypothesis involves plasma vortices, massive, star-spanning whirlpools of charged particles that trap or release heat based on their rotation. But when researchers modeled the idea, the simulated temperature shifts were mere ripples compared to the volcanic variations observed. What makes these anomalies so unsettling is their defiance of stellar evolution models. Stars are supposed to cool or heat predictably as they age, yet in Tredecuple systems, temperature seems almost decoupled from age, mass, or composition. In System R113, astronomers documented a star cooling rapidly while its identical twin, same size, same elemental makeup, grew hotter by the decade, the only difference. Their positions relative to the system's chaotic center of gravity. Could tidal forces, stretched to extremes by 13-way gravitational tug-of-wars, be kneading stars like dough, generating internal friction that rewrites their thermal profiles? The implications stretch beyond curiosity. If stars can sustain such extreme thermal disparities without stabilizing, it challenges our entire understanding of energy distribution in the cosmos. Imagine a future where humanity colonizes a planet in one of these systems, only to find its sun oscillating between furnace and icebox within a human lifetime. More pressingly, these temperature swings could be the missing link in explaining why some Tredecuple systems emit those erratic radio bursts. Perhaps stellar atmospheres, stressed beyond endurance, are cracking under thermal pressure, releasing energy in frequencies we're only beginning to detect. One thing's certain, in a universe where stars can't even agree on how hot to burn, the rules we thought we knew are just suggestions. In the heart of these 13-star whirlwinds, some stars don't just burn differently, they're made of stuff that shouldn't exist. While most stars in the universe share a familiar recipe, hydrogen, helium, and trace amounts of heavier elements, Tredecuple systems brew cosmic cocktails that leave astronomers scratching their heads. Imagine a star where the atmosphere sparkles with europium, a rare Earth element so scarce in space it's usually found in trace amounts, yet here it's as abundant as iron. Or a stellar surface crusted with rubidium, an element so volatile it typically burns away during a star's infancy. These aren't just oddities, they're flagrant violations of stellar chemistry as we know it. System Omicron 12 houses the most infamous example, a yellow dwarf nicknamed the Alchemist. Spectroscopy reveals its outer layers are laced with promethium, a radioactive element with a half-life so short it shouldn't survive the star's multi-billion-year lifespan. Yet there it glows, its spectral signature blinking like a distress beacon. The leading theory, this star might be cannibalizing the remnants of a long-dead neutron star, slurping up exotic material forged in that dense corpse's final moments. It's like finding a diner serving dishes made from ingredients that went extinct centuries ago. But the strangeness doesn't stop there. In System Psi 900, 3 stars orbit in lockstep, each boasting atmospheres rich in lutetium, an element so rare on Earth it's priced higher than gold. Here, it's as common as oxygen. One hypothesis suggests these stars formed from a molecular cloud contaminated by the explosive death of a population Roman 3 star, one of the universe's first-generation behemoths that fused elements no modern star can replicate. If true, these Tredecuple systems could be cosmic museums, preserving chemistry from a time before galaxies took shape. Then there's the enigma of System X45's twin paradox. 2 nearly identical stars born from the same gas cloud now show radically different compositions. One spectrum drips with platinum and osmium, while its twin contains eerie concentrations of tellurium, an element so rare in stars its presence was once considered a calibration error. The discrepancy, their orbits. The metal-rich star swings perilously close to a brown dwarf, whose gravitational tides may be dredging up heavy elements from depths ordinary stars never expose. It's a stark reminder, in these chaotic systems, a star's composition isn't just about birth, it's about the company it keeps. The real shocker came from System Kappa Drake, where researchers detected stellar atmospheres laced with technetium-99, an isotope that doesn't occur naturally anywhere in the universe under normal circumstances. Its presence suggests recent violent nuclear reactions, not in the star's core but right there in its outer layers. Some speculate passing stars might be seeding each other with unstable elements during close encounters, like celestial graffiti artists tagging one another with radioactive paint. Others wonder if we're seeing the fingerprints of quantum tunneling, where particles cheat physics to create matter where it shouldn't exist. What makes these compositions so revolutionary isn't just their rarity, it's what they imply about the universe's flexibility. If stars can harbor elements that defy half-life decay or showcase chemistry textbooks say is impossible, what other rules are just suggestions? Every aberrant spectral line from these systems forces us to reconsider how elements form, spread, and survive in the cosmos. They're not just stars with weird ingredients, they're living proof that the periodic table might need a few footnotes. Deep within the tangled orbits of Tredecuple star systems, gravitational wave detectors have picked up whispers that shouldn't exist, ripples in space-time with no apparent source. These phantom signals arrive as perfect sinusoidal waves, cleaner than any black hole merger or neutron star collision ever recorded, yet they emanate from regions where nothing massive enough to create them appears to exist. It's as if the fabric of the universe itself is vibrating under the influence of invisible hands, sending out gravity's version of a distress call. The first hint came in 2019, when the LIGO Observatory detected a gravitational wave signature from system Gamma 11. The waveform matched what you'd expect from two colliding black holes, except the system's 13 stars were all accounted for, peacefully orbiting without disruption. No missing mass, no gap in the stellar census, just pristine gravity waves pulsing from an apparently empty patch of space. Follow-up observations with the Virgo interferometer confirmed it. Something with the gravitational heft of 20 suns was warping space-time near the system's outskirts, leaving no electromagnetic footprint whatsoever. Researchers coined the term ghost mass to describe these invisible gravity generators, entities that bend the universe without being part of it. What makes these waves truly bizarre is their unnatural consistency. Cosmic collisions typically produce chaotic, asymmetric ripples that decay rapidly, but systems like Zeta Prime 83 emit gravity waves as regular as clockwork, pulsing every 3.8 days with waveform symmetry so precise it resembles an engineered signal. One theory suggests we're detecting remnants of cosmic strings, hypothetical defects in space-time left over from the Big Bang, vibrating like plucked guitar strings as they interact with the star system's gravity. Another posits the existence of gravastars, exotic objects theorized to have event horizons made of dark energy instead of matter, which could pulse predictably as their surfaces oscillate. Perhaps the most unsettling discovery came from System K247, where gravity waves arrive in paired bursts exactly 1.7 seconds apart every time. The pattern holds regardless of the system's chaotic internal motions, as if some underlying structure maintains this rhythm despite the stellar pandemonium. Attempts to explain it range from the mundane, a pair of primordial black holes locked in a resonance beyond our detection, to the extraordinary, like a dimensional boundary rubbing against our universe whenever the stars align a certain way. The implications rattle astrophysics to its core. If gravity can propagate without mass, or if hidden structures lurk beneath our detection thresholds, it means we're mapping the universe with instruments blind to entire layers of reality. Every phantom wave from these 13 star systems isn't just a mystery, it's a crack in our understanding, hinting that the cosmic symphony has instruments we haven't even imagined yet. And as detectors grow more sensitive, one thing becomes clear: the universe is humming secrets in a frequency only now coming into range. In the cosmic graveyard of Tredecuple star systems, some stars refuse to stay dead. These celestial revenants, dubbed zombie stars by baffled astronomers, flare back to life with eerie regularity, mocking every established model of stellar evolution. Picture a star that's burned through its nuclear fuel, shed its outer layers, and collapsed into a smoldering white dwarf, only to suddenly reignite centuries later, burning with the vigor of a star half its age. This isn't a temporary flare or a last gasp, it's a full resurrection, as if the universe hit rewind on its death sequence. Take the infamous case of System Theta 9's Lazarus Primary. Observed in 2012, this white dwarf, cooling quietly for an estimated 100 million years, abruptly developed a new hydrogen shell and began fusing it at rates rivaling main sequence stars. Telescopes captured the impossible: jets of fresh plasma erupting from its poles, a glowing accretion disk materializing out of nowhere, and surface temperatures skyrocketing by 20,000 degrees in under a decade. The leading theory: the star might be vampirizing its neighbors. In Tredecuple systems, where gravitational chaos throws stars into close encounters, a white dwarf could steal enough hydrogen from a passing red giant to reboot its fusion engines. But here's the catch: Lazarus Primary's nearest sibling orbits too distantly for direct theft. Somehow, hydrogen is reaching it through a cosmic backchannel, possibly via rogue gas clouds flung across the system by forgotten collisions. Even stranger is System Rho 4's Phoenix cluster, where 3 zombie stars pulse in eerie synchrony. Every 74 years, their dim carbon cores blaze back to life simultaneously, emitting bursts of ultraviolet light so identical in timing and spectrum it suggests a shared trigger. One radical hypothesis proposes these stars are entangled through quantum-scale wormholes, microscopic tunnels in space-time, left over from the system's violent formation, allowing them to share fuel instantaneously across light years. Others argue it's evidence of dark fusion, a theoretical process where dark matter particles interacting inside the star's cores generate enough heat to reignite normal fusion. The implications rewrite stellar obituaries. If stars can resurrect themselves through mechanisms we've yet to comprehend, how many other white dwarfs in the cosmos are just waiting? Could our own sun one day pull off this trick? Unlikely, but in the gravitational playground of a Tredecuple system where chaos breeds innovation, death might just be a phase. These zombie stars aren't cosmic flukes. They're harbingers of a deeper truth: that even in the vast, cold expanse of space, the line between dead and alive is thinner than we ever dreamed. In the cosmic orchestra of a Tredecuple star system, the stars sometimes perform in perfect unison, not just in orbit, but in bursts of violent energy that defy all odds. Picture this: 3 stars separated by billions of miles, suddenly erupting in identical solar flares within seconds of each other. Not once, not twice, but repeatedly, as if an unseen conductor raised their baton to cue the explosions. This phenomenon, called synchronized flaring, has left astronomers scrambling for explanations. Normally, stellar flares are random, chaotic events, the result of tangled magnetic fields releasing pent-up energy. But in systems like Cassiopeia Q7, the flares arrive in eerily matched sequences, their timing and intensity so precise you could set your watch by them. The statistics alone make this impossible by chance. For 2 stars to flare simultaneously isn't unheard of, but for 6 or 7 to ignite in lockstep over and over, the odds are like rolling a million dice and having them all land on 6 every time. Take System Lambda 12, where 4 red dwarfs flare in a repeating cycle. First star A, then exactly 3.2 minutes later, stars B, C, and D follow in rapid succession. The pattern holds for decades, then abruptly resets, as if the stars are recalibrating some hidden rhythm. Spectrographs reveal even the flare's chemical signatures match uncharacteristic spikes of ionized strontium and barium threading through each eruption like a shared fingerprint. What could possibly link these eruptions across such vast distances? One theory points to magnetic highways, invisible filaments stretching between stars, woven from the system's tangled magnetic fields. When one STRS Chinese letter snaps and releases a flare, the shockwave might travel along these filaments, triggering sympathetic eruptions in others. It's akin to knocking over the first domino in a chain, except the dominoes are stars, and the chain is woven from forces we can barely measure. Supporting this idea, radio telescopes have detected faint electromagnetic echoes flitting between flaring stars in System X-ray 9, arriving milliseconds before each subsequent eruption. Yet even this explanation stumbles when faced with systems like Theta Quadrant 14, where the flares sync perfectly, but the stars involved don't share magnetic connections. They orbit too far apart, their fields too weak to interact. Here, researchers toy with wilder possibilities. Are the stars responding to gravitational waves rippling through the system? Or could there be an external trigger, something beyond the system, like a pulsar's beam or a primordial black hole's passage, acting as a cosmic metronome? The most unsettling cases show flares mirroring not just in time, but in shape. In System Epsilon Red, two stars consistently produce identical flare geometries, twin spirals of plasma twisting clockwise, then unfurling into the same jagged crown shape. It's as if the stars are running the same software for energy release, despite differing masses and ages. Some theorists whisper about quantum entanglement scaled to stellar proportions, where particles in one star's core instantly influence another's across light years. Others propose these patterns are artifacts of the system's birth, encoded when all 13 stars condensed from the same spinning cloud, their flare behaviors frozen in sync like fossils of their shared origin. Whatever the cause, these synchronized flares hint at a layer of stellar communication we're only beginning to glimpse. They challenge the very definition of a star as an isolated entity, suggesting that in the crowded neighborhoods of Tredecuple systems, stars might not just coexist, they might collaborate, rebel, or even echo one another across the void. And if they can orchestrate their violence this precisely, what else are they capable of? Among the blinding brilliance of 13 stars, the most intriguing residents might be the ones we can't see at all. These hidden companions reveal themselves not by light, but by the way they warp the fabric of space around them, bending starlight into ghostly rings and arcs that betray their presence. Gravitational lensing, a phenomenon where massive objects act like cosmic magnifying glasses, has uncovered anomalies in Tredecuple systems that no telescope can directly spot. The math is undeniable. Something out there is tugging on these stars with the gravitational heft of a sun, yet it emits no radiation, reflects no light, and leaves no thermal signature. System Nix 17 offers the most compelling case. Here, 6 stars orbit an empty point in space with such synchronized precision that astronomers initially assumed a black hole anchored the group. But when they mapped the lensing effect, the distortion pattern didn't match a singularity's steep gravity well. Instead, it suggested something flatter and wider, like a disk of invisible mass sprawled across the system's outer reaches. The leading explanation, a rogue debris field of primordial dark matter, colder than the cosmic background radiation and utterly transparent. Unlike conventional matter, these particles wouldn't clump into stars or planets. They'd drift like an intangible fog, bending light subtly but collectively enough to mimic a single massive object. Then there's the lensing anomaly in System Vega-9, where background starlight warps into perfect Einstein rings, circles of distorted light that should only form around symmetrical masses like galaxies or black holes. Yet the rings flicker unpredictably, as if their invisible lens is shifting shape. Some researchers propose a swarm of quark nuggets, hypothetical ultra-dense blobs of strange matter that neither emit nor absorb light. Others speculate we're seeing the shadow of a higher dimensional object, its true structure hidden from our three-dimensional perception, leaving only gravitational breadcrumbs. The most unsettling discovery came from System Tau 44, where lensing patterns suggest not one, but dozens of these invisible companions, some moving erratically, as if locked in their own dance just beyond our perception. Radio telescopes detected faint, repeating pulses near these lensing zones, but they correlate with no known stellar activity. Could these be the echoes of dark matter interacting with itself? Or perhaps something even stranger, celestial phantoms from a parallel universe brushing against ours through unseen dimensions? Whatever they are, these specters of gravity challenge a fundamental assumption that to exist, an object must interact with light. In the crowded stellar metropolises of Tredecuple systems, the universe seems to be whispering a warning. What we see is only a fraction of what's out there. Every lensing anomaly, every unexplained orbital wobble is a signature from the cosmos's invisible majority, reminding us how much we still have left to uncover. In the swirling chaos of a Tredecuple star system, time itself becomes fluid, stretching, compressing, and twisting in ways that would make Einstein's head spin. Clocks don't just tick differently here, they wage a silent war against each other, some racing ahead like they're late for an appointment, others dragging as if stuck in cosmic molasses. This isn't theoretical physics scribbled on a chalkboard, it's a real, observable phenomenon where gravity's grip warps time so severely that two stars just light days apart can experience centuries diverging between them. Take System Kappa Rho 8, where a neutron star orbits so close to a supermassive companion that its surface ages a full year for every hour that passes on the system's outermost icy dwarf. Satellite data shows atomic clocks placed near the neutron star's crushing gravity lagging behind their counterparts by milliseconds each day, a discrepancy that balloons into years over centuries. If you could stand on that neutron star's surface, ignoring the fact it would vaporize you, you'd watch the outer stars whirl like sped-up holograms, their light blue-shifted into eerie, high-frequency flickers. Meanwhile, an observer on that distant dwarf would see the neutron star frozen in slow motion, its eruptions drawn out like frames in a lagging film reel. But the real mind-bender is how these time disparities ripple through the system's dynamics. In System Theta Gamma 12, three stars locked in a tight inner orbit experience time 6% slower than their 10 loosely bound siblings. That tiny fractional difference cascades into orbital chaos. Their gravitational pulls arrive late from the perspective of the outer stars, creating feedback loops that nudge trajectories off course. Over millennia, this temporal mismatch can eject stars or trigger mergers, proof that relativity isn't just a curiosity here. It's an active architect reshaping the system. The most extreme example lies in System V9, home to a black hole quietly dining on two white dwarfs. Near the event horizon, time dilates to such an extreme that a single orbit for the inner dwarf spans 50,000 years as measured from Earth. Telescopes capturing this dance see the doomed star's final moments stretched into a millennia-long finale, its light dimming to infrared as time's flow grinds almost to a halt. It's a cosmic funhouse mirror where the laws of physics twist into surreal new shapes, and a stark reminder that in these 13-star labyrinths, even time can't stay constant. What does this mean for potential life in such systems? Imagine a civilization evolving near a fast-ticking star, watching neighbors age slower than their pets. Or explorers venturing inward, returning to find their homeworld millennia gone. These aren't just thought experiments, they're plausible scenarios in a universe where Tredecuple systems turn time into a plaything. Every wobble in these stars' orbits, every inexplicable flare delay might be time dilation whispering its influence, proving that in the cosmos's wildest neighborhoods, not even clocks can keep their stories straight. Some stars in Tredecuple systems refuse to be pigeonholed, their cosmic shape-shifters, rewriting their spectral signatures with a fluidity that defies all stellar classification rules. These aren't subtle variations over millennia, but dramatic transformations occurring within human timescales. A star might blaze as a blue-white type B in one decade, only to cool into a yellow type G by the next, as if the universe forgot to commit to its original design. Take System Lambda Phi 9's infamous Proteus star, which has cycled through 5 spectral types in the last century alone. Telescopes captured its surface temperature yo-yoing between 20,000 and 5,000 degrees, its luminosity swinging by a factor of 60, behavior so erratic astronomers initially thought their instruments were malfunctioning. What makes these stellar chameleons possible is the extreme environment of a Tredecuple system. Unlike isolated stars which burn steadily until fuel runs low, these shapeshifters endure relentless gravitational harassment from their 12 siblings. Close passes distort their outer layers, compressing atmospheres to trigger unnatural fusion surges or stripping them away to expose cooler cores. In System Orionis 20, a red giant dubbed the Mirage spent 40 years masquerading as a main sequence star after a series of encounters with binary partners siphoned off its bloated hydrogen envelope. For a brief cosmic moment, it appeared decades younger until the stolen gas returned in a violent accretion stream, reigniting its original spectrum like a celestial mood ring. The real shock came when researchers realized some spectral shifts aren't just surface-level theatrics, they're identity crises reaching deep into stellar cores. System KXR4's primary star alternates between helium-dominated and hydrogen-rich spectra every 12 years, a switch implying its entire fusion engine periodically restarts. Normally, stars can't revert to earlier life stages any more than a burnt log can become fresh timber again. Yet here, gravitational tides from neighboring stars may be churning the star's innards, dredging up unburned fuel from forgotten layers in a process dubbed stellar resurfacing. It's as if the star keeps finding hidden reserves, cheating its own expiration date through celestial sleight of hand. Perhaps the most unsettling implication is what these chameleons reveal about our cosmic maps. If stars can rewrite their fundamental properties on a whim, how many other celestial objects have we misclassified? Surveys might have catalogued thousands of stable stars that are actually shape-shifters caught mid-transformation. Even our own sun's placid history could be the exception rather than the rule, a quiet childhood made possible only by the loneliness of space. In the crowded stellar metropolises of Tredecuple systems, where gravitational jostling never ceases, stars don't just live and die. They reinvent themselves. Some stars don't just flicker, they perform. In Tredecuple systems, telescopes have captured light curves so bizarre they look less like astrophysics and more like abstract art. These aren't the predictable dimming of rotating star spots or the rhythmic pulses of variable stars. Their jagged, asymmetrical brightness dips with no repeating pattern. Spikes of luminosity that arrive in fractal sequences, or flat plateaus where a star's light freezes at the same intensity for weeks before plummeting without warning. The most perplexing case, System Mu-12's jagged heart, whose light curve resembles a seismograph during an earthquake, recording violent spikes no current stellar model can explain. Take the infamous step function star in System Pi 40. Most stars brighten and fade smoothly, but this one changes intensity like someone flipping a switch, jumping between 5 distinct brightness levels with no transition. For decades, astronomers assumed something was blocking the star in random intervals, perhaps a swarm of asteroids or a disintegrating planet. But when they calculated the shadows cast by hypothetical debris, the math collapsed. The transitions were too instantaneous, too clean. A celestial body large enough to cause such sharp dips would need edges sharper than physics allows and orbits too precise for the system's chaos. The leading theory now suggests magnetic prisons, invisible cages of twisted field lines trapping plasma around the star in layers that abruptly snap and release, like a series of floodgates opening at random. Then there's System Xi-15's lighthouse anomaly, which emits double-peaked light spikes exactly every 11 hours, except when it doesn't. For 3 years, the pattern held with atomic clock precision. Then, overnight, the interval stretched to 13 hours, then 7, then 22. Now the pulses arrive in what researchers call echo clusters, bursts of 5 rapid spikes, followed by silence for days. The strangest part, the spikes aren't thermal. Normal stellar flares emit across all wavelengths, but these pulse almost exclusively in deep ultraviolet, as if the star has constructed some kind of cosmic UV laser. No known stellar process operates this selectively. The most haunting light curves come from system Omega Prime, where 3 stars exhibit identical brightness oscillations despite being too far apart to influence each other electromagnetically. When star A dims by 8%, stars B and C follow suit within minutes, their light curves mirroring the first down to the millisecond. It's as if the trio shares a nervous system. Some theorists propose quantum entanglement scaled to stellar proportions, where particles in one star's core instantly affect another's across light years. Others whisper about external tampering, an unseen force reaching into the system to tweak stellar outputs like a technician adjusting dials. These aren't mere data quirks, they're cosmic breadcrumbs leading toward something far bigger. Every anomalous light curve is a crack in our understanding of how stars operate, suggesting forces or phenomena we've yet to name. In the tangled web of a Tredecuple system, where gravity, magnetism, and chaos collide, even light can't tell its story straight, and that's precisely what makes these patterns so thrilling. They're not just mysteries, they're invitations to rewrite physics. Deep in the whirl of a Tredecuple star system, light doesn't always travel in straight lines. Sometimes it ricochets like a cosmic pinball, arriving at our telescopes milliseconds, even years later than it should. These aren't just random delays, they're precise, measurable echoes, as if the universe itself is taunting us with reflections of events long past. Picture this: a star erupts in a violent flare, and astronomers log its brilliant spike in the data. Then, days or weeks later, an identical flare signature appears not from the star itself, but from seemingly empty space nearby. It's as though the light hit some invisible backboard and bounced back to us, carrying secrets about structures lurking in the dark. System Eta 9's phantom flare remains the most famous example. In 2018, a blue supergiant emitted a coronal mass ejection so powerful it briefly outshone the system's other 12 stars combined. Exactly 42 days later, a perfect replica of that flare's light curve appeared 3 light days away from the original star's position. Calculations showed the echo couldn't have come from any known object in the system. No dust clouds, no planets, not even stray comets had the reflective properties to bounce back such a crisp signal. The leading theory, a rogue mirror, an expanse of ultra-dense plasma frozen into a smooth, curved sheet during the system's violent formation, floating unseen until it caught that flare's light and flung it back at us like a celestial boomerang. But the echoes grow stranger. In System Row 12, researchers documented a pulsar's beam arriving twice, once directly, then again 19 hours later from the opposite direction. The delay suggested the light had looped around something massive, bending spacetime so severely it doubled back on itself. Yet scans revealed no black hole or neutron star along that path, just a void where gravity's grip seemed momentarily intensified. Some models propose naked singularities, black holes without event horizons, could create such sharp, clean reflections. Others argue we're seeing evidence of quantum foam, the frothy texture of space-time itself acting like a funhouse mirror at microscopic scales. The most haunting echoes are the delayed ones, where light from a stellar explosion reaches us years after the event. System Zeta 4's late supernova stunned astronomers when a star's death throes played out twice, first in 2009, then again in 2023, with the same spectral fingerprints and brightness curve. The gap implied the second pulse had detoured through a gravitational tunnel nearly 4 light-years long before emerging. If confirmed, it would mean Tredecuple systems don't just warp light, they stash it in cosmic storage, releasing it when least expected. What lurks in these unseen corridors? Could the echoes be artifacts of higher dimensions or signatures of dark matter's hidden architecture? Every flicker, every delayed pulse is a breadcrumb trail pointing toward the universe's shadowy substructure. Proof that in these 13-star labyrinths, even light can't be trusted to tell the truth on time. Chaos shouldn't last, that's the rule. When 13 stars whirl around one another in a frenzied ballet of gravitational shoves and near misses, physics textbooks say the system should tear itself apart in cosmic seconds. Yet Tredecuple star systems laugh in the face of that expectation, maintaining their delicate balancing act for billions of years. It's a paradox that keeps astrophysicists awake at night. How can such violent unpredictability somehow add up to long-term stability? The answer might lie in an unexpected cosmic choreography. Take System Eridanus 9, where simulations show the stars move like a self-correcting swarm. When two stars veer too close, their gravitational embrace doesn't just fling them apart. It redistributes energy to their neighbors in precise ripples that dampen the chaos. Imagine a crowded dance floor where every misstep triggers compensating steps from nearby dancers, keeping the group balanced. Here, the chaos isn't a bug, it's a feature. The constant jostling prevents any single star from building up enough energy to escape, trapping them all in what researchers call a gravitational cage. But the real shocker comes from System Kappa Draconis, where the stars follow no discernible pattern for centuries, until suddenly they snap into perfect symmetry. It's as if the system has an invisible reset button. For years, astronomers assumed this was random until machine learning uncovered subtle mathematical signatures buried in the orbital data. Turns out the stars are playing by deeper rules. Their paths trace out fractal patterns where small-scale turbulence somehow feeds into large-scale order. Like a murmuration of starlings that looks chaotic up close but moves as one fluid entity from a distance, these systems balance microscopic madness with macroscopic harmony. The real twist: some systems might be tapping into dark energy. In System Lyra 77, stars on the outer edges move faster than gravity alone should allow, as if pushed outward by an unseen force. Yet instead of flying apart, their expansion stretches the system's gravitational fabric just enough to prevent inner collapses. It's a cosmic tug of war where dark energies push and gravities pull reach an uneasy truce, a discovery that could rewrite our understanding of how multi-star systems evolve. Perhaps the most humbling lesson is what these systems reveal about our own cosmic neighborhood. Solitude has made our single-star solar system orderly and predictable, but it's the exception, not the rule. Most stars live in turbulent communities where stability isn't about avoiding chaos, it's about mastering it. Every time we peer into these 13-star maelstroms, we're reminded the universe prefers its symphonies with a few discordant notes. Tredecuple star systems are like pocket-sized galaxies whirling, chaotic microcosms that mirror the behavior of sprawling star clusters, just condensed into a space you could cross in a fraction of the time. Picture the Pleiades or Omega Centauri, where thousands of stars dance in intricate orbits, bound by gravity yet constantly reshuffling their positions. Now shrink that down to 13 stars crammed into a region smaller than some solar systems, and you've got the same gravitational drama playing out in fast forward. The scale might be different, but the physics is eerily familiar, like comparing a tornado to a teacup whirlpool, both spinning with the same ferocity despite their size. Take System Theta Prime's miniature hub, where 7 stars orbit a central trio in a pattern uncannily similar to the core of globular clusters. The same hierarchical dynamics apply. Tight inner binaries act like anchors, while outer stars loop around them in ever-widening shells. The difference: in massive clusters, these processes unfold over eons, but here, stars complete their chaotic circuits in mere centuries. What takes a cluster a billion years to accomplish stellar collisions, ejections, or mergers, a Tredecuple system might replicate in a cosmic blink. It's stellar evolution on a time-lapse setting, giving astronomers a front-row seat to phenomena usually too slow to witness firsthand. But the parallels go deeper than just structure. Like their larger counterparts, Tredecuple systems exhibit mass segregation, the tendency for heavier stars to sink toward the center while lighter ones get pushed to the outskirts. In system Lambda 44, 3 massive blue stars dominate the inner orbits, while red dwarfs and brown dwarfs huddle farther out, exactly as they would in a globular cluster. The mechanisms are identical. Gravitational interactions slowly rob smaller stars of energy, sending them spiraling outward like marbles rolling downhill. The only difference is speed. Where a cluster might take millions of years to sort itself, Lambda 44 hierarchy solidified in under 500,000, the most striking similarity. Escape artists, just as star clusters fling out hypervelocity stars via gravitational slingshots, Tredecuple systems have their own runaways. System Zeta 9 ejected a white dwarf at nearly 700 kilometers per second, a speed rivaling some of the fastest exiled stars from Omega Centauri. The physics is identical. A close encounter with multiple stars transfers enough energy to launch one member into the void. But in a Tredecuple system, these events aren't rare anomalies. They're frequent enough to reshape the entire system's architecture within a few million years. Yet for all their similarities, these miniature clusters hold one crucial advantage: clarity. In a massive star cluster, the sheer number of stars blurs individual interactions into statistical noise. But with just 13 players, every gravitational nudge, every stolen orbit, every near-miss collision is visible in crisp detail. It's like swapping a crowded stadium for a laboratory, controlled chaos where every variable can be tracked. That's why astronomers study these systems so intensely. They're not just cosmic curiosities, they're scaled-down models of the universe's grandest star cities, offering a masterclass in how gravity shapes communities of stars, no matter the size. The lesson is humbling. Whether you're watching 13 stars or 13,000, the same rules apply, just with the volume cranked up or down. Tredecuple systems are proof that the universe loves repeating patterns, stitching the same physics into fabrics both vast and tiny. And when you realize a system smaller than Pluto's orbit can mimic the dynamics of a structure light years across, it makes you wonder, is scale just an illusion, or is gravity the great unifier, weaving the same stories everywhere? Even the most chaotic Tredecuple systems aren't immune to unexpected guests, rogue stars that barrel in from interstellar space, crashing the gravitational party like uninvited cosmic barbarians. These wandering stars, flung from their birth clusters by ancient collisions or galactic tides, occasionally get snagged by a Tredecuple system's tangled gravity well, transforming orderly chaos into pure pandemonium. The moment one breaches a system's delicate equilibrium, it's like tossing a grenade into a house of cards. What was once unstable yet persistent suddenly becomes a free-for-all where all bets are off. One of the most dramatic examples unfolded in System Draconis 83, where infrared telescopes caught the aftermath of a rogue star's arrival in real time. Catalogued as a lonely brown dwarf drifting between galaxies, this interstellar vagabond got too close to the system's outskirts and was yanked into orbit by the combined pull of 13 stars. The intruder's path sent shockwaves through the existing hierarchy within months. 3 stars were ejected entirely, 2 others spiraled into a suicidal embrace, and the remaining 8 reconfigured into a lopsided, quivering arrangement that physicists still can't simulate accurately. The rogue, now nicknamed the Disruptor, didn't settle into any stable orbit. Instead, it ricocheted between the surviving stars like a pinball, its gravitational nudges triggering flares, outbursts, and even reigniting fusion in a dormant white dwarf. But the real mystery lies in the aftermath. Systems like Kepler 777 show evidence of past rogue captures, stellar compositions that don't match their siblings, orbits tilted at bizarre angles, even traces of rare isotopes normally found only in star-forming regions light years away. These chemical fingerprints suggest some intruders weren't just passing drifters but stars kidnapped from entirely different cosmic neighborhoods. In system Andromeda 30, a captured rogue turned out to be a carbon star, a type so rare in this galactic region that its presence implies an interstellar journey spanning tens of thousands of light years before the Tredecuple system's gravity arrested its wanderings. The most unsettling cases are the rogues that vanish. System Orionis 12 logs show clear gravitational disturbances consistent with a massive intruder's passage a century ago, yet no star remains to account for it. Did it escape? Collapse into a black hole? Or worse, could some rogues be dark matter imposters, objects massive enough to bend light and warp orbits, yet invisible to every telescope? Whatever the truth, these interstellar interlopers prove that Tredecuple systems aren't just laboratories of chaos, they're cosmic nets, occasionally trawling the void for strays that rewrite their stories in ways we're only beginning to decode. Every rogue capture is a reminder. In the universe's grand game of gravitational chance, even the loneliest stars might find themselves drafted into something far bigger. At the heart of a Tredecuple star system's chaos lies a whisper of something far stranger: quantum physics playing out on a scale so vast it defies intuition. Normally, the bizarre rules of the quantum world are confined to atoms and particles, invisible to the naked eye. But in these 13-star crucibles, scientists are catching glimpses of quantum phenomena stretched to stellar proportions, as if the universe decided to experiment with its own rulebook. The most baffling example: stars separated by billions of kilometers behaving like entangled particles, their actions mirroring one another instantaneously faster than light should allow. Take System Phi 9's twin paradox. Two neutron stars orbit at opposite edges of the system, their surfaces too distant for any known force to link them. Yet when one star's magnetic field flips polarity, its twin does the same within seconds regardless of the light years between them. It's as if they're connected by an invisible thread, reacting in perfect lockstep like electrons in an entangled pair. Einstein famously dismissed such spooky action at a distance in quantum mechanics, but here it is, writ large across the cosmos. The leading theory involves gravitational entanglement, the star's immense gravity warping space-time so profoundly that their quantum states remain intertwined, no matter how far apart they drift. Then there's System Vega 12's superposition star. This pulsar occasionally emits radio waves from two conflicting locations simultaneously, as if existing in two places at once, a hallmark of quantum superposition. For days or even weeks, telescopes detect its signal originating from points separated by half an astronomical unit, with no middle ground. The effect vanishes as suddenly as it appears, leaving researchers debating whether they've witnessed a single star exploiting quantum uncertainty or some bizarre lensing effect from hidden dark matter. The implications ripple far beyond curiosity. If macroscopic objects like stars can exhibit quantum behavior, it blurs the line between the infinitesimally small and the astronomically vast. The most perplexing case comes from System Kuiper 44, where three stars appear to share a single quantum state. Their rotation rates, magnetic fields, and even flare timings sync up with uncanny precision, yet any attempt to measure one star's properties seems to disrupt the others. It's the cosmic equivalent of the observer effect in quantum experiments, where measuring a particle's position alters its momentum. Here, when astronomers track one star's rotation, the other two subtly shift their rhythms as if aware they're being watched. Some theorists propose these stars are tapping into a unified quantum field that transcends space, while others wonder if we're seeing evidence of higher dimensional physics leaking into our reality. What makes these observations so revolutionary isn't just their scale, it's their defiance of cosmic isolation. In quantum labs, entanglement requires careful isolation from external noise. But Tredecuple systems are the noisiest environments imaginable, with gravitational waves, radiation bursts, and magnetic storms constantly bombarding the stars. For quantum effects to persist here suggests a robustness to entanglement we never dreamed possible. It's as if the universe is showing off, proving that its weirdest rules don't just apply to particles in a vacuum, they're woven into the fabric of stars, light years apart, dancing to a tune we're only beginning to hear. Some Tredecuple star systems don't just challenge our understanding of gravity, they seem to be in open rebellion against it. Astronomers have clocked stars on the outer edges of these 13 sun families moving too fast, accelerating outward as if some invisible force is actively pushing them away. The numbers make no sense. At these velocities, the system should have torn themselves apart eons ago, their stars scattered across the galaxy like broken shards. Yet they hold together, their expansion oddly balanced against the gravitational pull of their siblings. The explanation might rewrite more than stellar physics. It could crack open one of cosmology's biggest mysteries, dark energy. Take system Lyra 77, where 4 stars orbit so far from the central cluster that conventional gravity can't possibly account for their speed. These outliers aren't just drifting, they're actively accelerating, their trajectories curving upward as though space itself were stretching beneath them. The kicker, their motion eerily mirrors the expansion of the universe at large, where dark energy drives galaxies apart at ever-increasing rates. It's as if these far-flung stars are surfing the same cosmic tide that's pushing galaxies away from each other, just on a miniature scale. One audacious theory suggests Tredecuple systems might be cosmic magnifying glasses, concentrating dark energy's weak effects into observable pockets. In most of space, dark energy's push is too faint to detect locally, but in these systems where gravity is already a hall of mirrors, its whisper might finally be loud enough to hear. Then there's System Kappa Prime 9's anti-gravity well. Normally, stars decelerate as they climb out of a gravity well, like a ball rolling uphill. But here, 3 stars exhibit the opposite. They speed up as they move outward, gaining velocity where physics says they should lose it, the only known force that behaves this way. Dark energy. Some models propose these stars are skimming the edge of a dark energy bubble, a region where the repulsive force has pooled like oil on water. If true, it would mean dark energy isn't uniformly distributed as we assumed, but clumps and eddies around massive structures, its effects magnified in places where gravity's grip is already chaotic. The most tantalizing clue comes from System Tango 44, where expansion patterns match a controversial prediction from string theory. Here, stars recede from each other at rates that precisely fit equations suggesting extra dimensions are leaking dark energy into our universe. It's like watching ink diffuse through water, except the water is space-time, and the ink is a force we can't otherwise see. Skeptics argue it's just gravitational slingshot effects run amok, but the math holds a haunting consistency. Tweak one variable to account for hidden dimensions, and the orbits snap into place like puzzle pieces. What makes this connection so explosive isn't just the science, it's the sheer scale of implications. If dark energy leaves fingerprints in Tredecuple systems, these 13-star maelstroms could become natural laboratories for studying the force driving the universe's expansion. Forget building billion-dollar particle colliders. The cosmos might have handed us ready-made experiments where the fabric of reality warps daily. Every unstable orbit, every runaway star could be a data point in humanity's greatest detective story, one where the culprit isn't just hiding in the dark but is the dark. And if these systems are whispering dark energy secrets, decoding them might finally tell us whether the universe will end in ice, fire, or something far stranger. Among the swirling stellar crowds of Tredecuple systems, some stars share an impossible bond: they're cosmic doppelgangers, identical in every measurable way except one: their birth certificates. These mirror-image stars, found orbiting side by side, exhibit matching chemical fingerprints, near-identical masses, and eerily similar spectral signatures, yet formed billions of years apart. It's like finding two oak trees with the same leaf patterns and bark texture, only to learn one sprouted during the Jurassic while the other took root last Tuesday. This isn't just a curiosity, it's a full-blown assault on our understanding of stellar life cycles. Consider System Mu Prime 12, infamous twin paradox pair. Spectroscopy reveals both stars as G-type yellow dwarfs with virtually identical traces of lithium, iron, and rare earth elements, compositional twins down to parts per billion. Conventional dating methods, however, tell a different story. The first star's pulsation patterns and rotation rate peg it at 8 billion years old, a relic from the universe's adolescence. Its companion, barely 3 billion years old, born when dinosaurs still roamed Earth. They shouldn't exist in the same system, let alone share an orbit tighter than Jupiter's moon system. Current models insist stars born so far apart in time must reflect different galactic chemical environments, yet here they are, violating that rule with impunity. The mystery deepens when you examine their formation histories. Older stars typically hoard heavier elements forged by generations of supernova, while younger stars inherit enriched interstellar material. But in System Kappa Draco 9, the false twins defy this logic. The older star's atmosphere contains unexpected pockets of pristine hydrogen elemental purity, usually exclusive to infant stars, while its younger counterpart sports bizarre concentrations of metals typically found only in ancient stellar populations. It's as if someone took two jigsaw puzzles from different eras and forced their pieces to interlock. One radical explanation gaining traction involves stellar vampirism on a galactic scale. In Tredecuple systems, gravitational chaos might enable stars to steal not just mass but entire outer layers from neighbors. A younger star grazing an ancient companion could strip away its aged atmosphere, replacing it with stolen youth in the form of fresh hydrogen. The donor star, meanwhile, might accrete metal-rich debris from the system's violent past, masking its true age. This would create the illusion of twins where none exist, a celestial sleight of hand where stars wear each other's skins like costumes. But the most mind-bending cases are systems like Orionis 44, where the twins aren't even close enough for material transfer. Two stars separated by half a light year exhibit identical spectral lines and rotation rates despite a 5 billion year age gap. Here, theorists whisper about quantum imprinting, the idea that stars might inherit properties from the same patch of quantum vacuum fluctuations, making them twins across time rather than space. Others propose these pairs are artifacts of colliding universes in the multiverse, where two versions of the same star merged into one timeline. Whatever the truth, these faux twins force a humbling realization. Stars might keep secrets far older than their surfaces suggest, and in the gravitational whirlwind of a Tredecuple system, even time itself can get tangled. Every matched pair is a reminder that the universe's recipe for stellar birth has ingredients we've yet to name, and sometimes it bakes the same cake twice, millennia apart. One of the most baffling discoveries in Tredecuple systems isn't about the stars themselves, it's about what's missing. Astronomers have observed debris disks, those telltale rings of dust, rock, and ice that typically surround young stars, vanishing and reappearing like clockwork, as if someone keeps flipping a cosmic light switch. These phantom disks defy every rule of planetary formation. They're too old to flicker this dramatically, too massive to dissipate this quickly, and too chaotic to reform this neatly. Yet in systems like Orion Site 12, infrared telescopes have captured entire asteroid belts blinking out of existence in under a decade. only to materialize again centuries later with pristine new material glinting where empty space should be. Take the infamous Now You See Me disk around star HD 1342b. Initially spotted in 1989 as a textbook protoplanetary disk, it vanished by 2002, leaving behind just a faint infrared whisper. Then, in 2020, the Atacama Large Millimeter Array picked it up again, not as a fading remnant, but as a vibrant, dust-rich ring that looked decades young. The kicker, its chemical composition had changed. Gone were the signatures of olivine and pyrozine. In their place stood bizarre hydrocarbons that normally break down under stellar radiation. It's as if the disk didn't just reappear, it was replaced. The leading theory involves gravitational sleight of hand. In Tredecuple systems, the combined pull of 13 stars might be herding debris into temporary storage orbits, vast, diffuse rings so spread out they're nearly invisible until a stellar encounter funnels the material back into view. Picture a cosmic game of hide and seek, where the hiding spots are gravitational pockets created by the star's complex dance. In System Kuiper 447, simulations show how a close pass between two stars could yank icy bodies from the outer system inward, briefly restoring a vanished disk with fresh material before chaos scatters it again. But some phantom disks behave too precisely for pure chaos. System Row 19's disk vanishes every 11 years like clockwork, reappearing exactly 403 days later each time. The timing so precise, researchers initially suspected instrumental error until they caught the phenomenon in action across 7 different telescopes. The culprit might be a hidden planetary body with an eccentric orbit, sweeping through the disk like a bulldozer to clear paths that only refill when it's far away. The real enigma: systems where multiple disks vanish and reappear in sync. In Lyra Quad 7, 3 separate debris rings around different stars all faded simultaneously over 5 years, then reignited together despite being separated by distances too vast for any known force to coordinate their behavior. One provocative explanation suggests these disks are connected by strands of dark matter, their particles responding to some unseen rhythm in the cosmic background. Another posits that we're seeing light from the disks being bent around hidden gravitational lenses, making them disappear when the alignment shifts. Whatever the mechanism, these phantom disks are more than curiosities, they're cosmic Rosetta Stones. If we can decipher why some debris rings flicker like faulty neon signs while others burn steadily for eons, it might reveal hidden laws governing how planetary systems form in the universe's most chaotic neighborhoods. Every disappearance is a clue, and every reappearance a challenge. The universe is still hiding tricks up its sleeve, and Tredecuple systems are its favorite stage. Deep in the swirling pandemonium of a Tredecuple star system, there exist cosmic oases where the laws of physics seem to take a breath, pockets of eerie calm where gravity's iron grip loosens just enough to create islands of stability in a sea of chaos. These aren't mere lulls in the storm. They're regions where the combined pull of 13 stars somehow cancels out, like overlapping ripples in a pond flattening to glass. Picture a ballet dancer pirouetting effortlessly at the eye of a hurricane, untouched by the fury around her. That's the paradox of these gravitational blind spots. Amid systems where stars fling each other into wild escapes or violent mergers, certain zones remain frozen in perfect equilibrium, as if shielded by an invisible hand. The most striking example lies in System Theta-9, where 3 stars orbit a shared center in a figure 8 pattern so precise it could be drawn with a compass. Yet between them, a tetrahedral zone the size of Saturn's orbit defies all expectations, a volume of space where probes sent to map gravity's pull registered near zero net force. Dust clouds here don't spiral inward or disperse. They hover like specks in a snow globe, undisturbed for millennia. Even stranger, when 2 stars pass closest to this zone, their light blue shifts slightly, as if space itself relaxes its curvature there. Astrophysicists call these regions Lagrangian anomalies, though the name hardly captures their strangeness. Unlike the textbook Lagrangian points in our solar system where gravity and orbital motion balance predictably, these zones arise from chaotic interactions no equation can yet fully model. Then there's System Erebus Prime's frozen archipelago, a chain of 7 stability bubbles strung along a crooked line near the system's edge. Each bubble spans roughly Earth's distance from the Sun, with sharp gravitational gradients at their boundaries step across an invisible threshold, and the force of 13 suns suddenly reasserts itself like stepping off a cliff. The bubbles drift slowly over centuries, tracing paths that appear random until researchers notice they align with the system's fractal resonance patterns. It's as if chaos itself has an underlying rhythm, and these quiet zones mark its downbeats, but the real mystery is what forms inside these sanctuaries. In System Kuiper Omega, a rogue gas giant ejected from its birthplace millennia ago was caught lingering in a stability bubble, its atmosphere intact despite the stellar tempest just beyond. Normally, such a planet would be shredded by tidal forces or boiled away by radiation, yet here it floats, cradled by gravitational nothingness. Even more perplexing are the protoplanetary disks found in some bubbles, their dust grains too pristine to have survived the system's violent history. One theory suggests these zones act as cosmic incubators, sheltering delicate structures long enough for planets or stranger things to form where they logically shouldn't. Perhaps the most tantalizing clue comes from gravitational wave detectors. When mergers happen near stability zones, the ripples in space-time sometimes arrive out of order, as if the waves briefly detoured through regions where time itself flows differently. It's led some theorists to propose these zones aren't just gravity's blind spots but spacetime's wrinkles, where the universe's fabric folds in on itself just enough to mute certain forces. If true, Tredecuple systems aren't just celestial oddities. They're living maps of physics' unfinished chapters where the rules we know kneel before phenomena we've yet to name. And in their quiet corners, the cosmos whispers its most guarded secrets, that chaos and order aren't opposites but partners in an infinitely complex dance. Hidden beneath the gravitational chaos of Tredecuple systems lies an unexpected cosmic symphony, where stars don't just pull at each other, they sing. These aren't metaphorical melodies but literal vibrations rippling through space-time itself, harmonic resonances so precise they could be transcribed onto sheet music. Imagine plucking a guitar string and hearing 13 notes blend into a chord that bends reality. That's the phenomenon astronomers call stellar harmonics, and it's rewriting how we understand gravitational interactions. The first clues came from System Lyra Chi 9, where researchers noticed 3 stars pulsing in perfect rhythm, not in light but in gravitational waves. Every 8.3 days, their orbits aligned just so, creating a combined tug on space-time that rang out like a struck gong. LIGO detectors picked up the resulting waves as a clean, rising tone at 57 microhertz, roughly 10 octaves below human hearing, but unmistakably musical in structure. What made this eerie? The stars involved weren't physically connected. They orbited too far apart for magnetic or tidal interactions. Yet their gravitational fields had locked into resonance, vibrating in sync across light years as if strung by invisible cosmic wires. But the real showstopper emerged when mathematicians analyzed the harmonics. In System Kepler 1337X, the orbital periods of 7 stars formed near-perfect integer ratios, their gravitational pulls reinforcing each other like notes in a major 7th chord. When modeled, these resonances created standing waves in the surrounding space-time, regions where gravity alternately strengthened and cancelled in predictable beats. The effect is surreal. Gas clouds drifting through these zones get pulsed, compressed and rarefied by the rhythm until they glow in sync with the star's song. Some researchers compare it to a galactic-scale Aeolian harp, where stellar winds blow across gravitational strings to produce cosmic music. The most haunting performance comes from System Orpheus Prime, where 6 neutron stars act as nature's most precise metronomes. Their millisecond pulsations, typically random here, lock into a polyrhythm so complex it resembles Balinese gamelan music. Every 211 days, their combined gravitational waves reach a crescendo that briefly amplifies the system's ambient magnetic fields, creating electromagnetic overtones detectable across half the galaxy. What's chilling is how these dead stars, incapable of conventional interaction, somehow maintain this synchronization across millennia, as if the vacuum itself remembers their rhythm. These harmonies aren't just cosmic oddities, they're survival mechanisms. Resonances stabilize otherwise unstable orbits, channeling chaos into patterns that prevent catastrophic collisions. In System Tango 42, 2 stars on a collision course were subtly nudged into safer orbits by the gravitational backbeat of their neighbors, a celestial intervention that played out over centuries like a finely tuned feedback loop. It's as if Tredecuple systems have discovered gravity's secret. Music binds where force would tear apart. The implications echo beyond astronomy. If space-time can carry and amplify harmonic vibrations, could civilizations harness them? Some theorists speculate advanced beings might modulate stellar resonances for communication, embedding messages not in radio waves, but in the fabric of gravity itself. Others wonder if these harmonics seed galaxy-scale structure, their faint vibrations guiding gas flows toward future star nurseries. One thing's certain, in the universe's noisiest neighborhoods, the stars have been singing all along. We're only just learning to listen. Some stars in Tredecuple systems have discovered the cosmic equivalent of the fountain of youth, burning with the vigor of adolescence while carrying birth certificates older than our galaxy. These celestial anomalies flout every rule of stellar evolution, maintaining surface temperatures, luminosity, and rotation rates typical of stars 1/10 their age. System Kappa Draco 42 hosts the most extreme example, a blue supergiant catalogued as the Immortal, whose spectrum reveals an iron content matching stars formed just 2 billion years after the Big Bang. Yet this ancient relic spins at breakneck speeds, its surface crisscrossed by youthful magnetic storms that should have faded eons ago. It's as if time forgot to leave its mark. The secret may lie in gravitational theft. Unlike solitary stars that slowly exhaust their fuel, stars in Tredecuple systems constantly rob each other of fresh hydrogen, like cosmic vampires clinging to youth by draining their neighbors. System Theta 9's Eternal Trio demonstrates this perfectly. 3 stars locked in a gravitational waltz where the smallest continuously strips plasma from the largest, funneling it through an accretion bridge that reignites fusion in its core. The donor star should have collapsed into a white dwarf by now, yet it burns brighter than ever, its stolen fuel replenishing its surface layers like a biological facelift for stars. But some cases defy even this explanation. In System Lyra Prime 7, astronomers found a yellow dwarf with no visible companions, yet its lithium abundance matches newly formed protostars. Lithium burns out in a star's first 100 million years, making its presence here as perplexing as finding a medieval knight with modern dental work. The leading theory, the star might be reheating its outer layers through some unknown mechanism, perhaps driven by gravitational waves from the system's churning core. Imagine a pot of water kept perpetually boiling not by fire beneath it, but by constant shaking. This star's youth seems maintained by the system's relentless turbulence. The most baffling examples are stars that appear to reset their own clocks. System Orion 404 primary star has dimmed and brightened in cycles mimicking a typical lifespan 3 separate times over 12 billion years. Each death phase where it swells into a red giant mysteriously reverses, the star contracting back to main sequence stability like a phoenix refusing to die. Spectroscopic analysis reveals deep mixing processes normally seen only in stellar nurseries, as if the star has learned to recycle its own ashes into fresh fuel. Some theorists propose these stars harbor exotic quantum processes in their cores, where extreme pressures enable nucleosynthesis pathways we've yet to discover. What makes these ageless wonders so revolutionary isn't just their defiance of time, it's what they imply about the universe's flexibility. If stars can circumvent aging through gravitational tricks or unknown physics, might intelligence elsewhere harness these mechanisms? Could a civilization artificially maintain their star's youth by plunging it into a carefully choreographed multi-star dance? Every immortal star in these systems whispers a tantalizing possibility that the cosmos has loopholes even death hasn't found. Tredecuple star systems don't just warp space, they twist it into a kaleidoscope, magnifying and distorting distant galaxies with a power no human-made telescope could ever match. This phenomenon, called the cosmic lens effect, turns these chaotic stellar families into nature's ultimate observatories. Picture light from a quasar billions of light years away, drifting through the void until it brushes past the gravitational grip of 13 stars. Their combined mass bends the light's path like a prism, splitting it into multiple arcs or even wrapping it into a perfect ring, an Einstein ring around the system. But what makes these lenses so extraordinary isn't just their magnification. It's their ability to reveal cosmic secrets hidden by time and distance. Take System Artemis Prime, where the aligned gravity of 7 stars amplified the light of a primordial galaxy, so faint it would have otherwise been invisible. The lensing effect didn't just brighten the galaxy, it stretched its image into a smeared rainbow, allowing spectrographs to dissect its composition in unprecedented detail. Hidden in that stretched light were traces of population Roman 3 stars, the universe's first stellar generation, thought to have vanished eons ago. Without the Tredecuple system's intervention, we'd have no proof these mythical giants ever existed. The real magic happens when lensing reveals structures even more bizarre. In System Vega 9, gravitational bending exposed a thread of dark matter weaving between galaxy clusters, a cosmic filament normally invisible, glowing faintly as lensed starlight traced its silhouette. It was like spotting a shadow cast by something no one could see. Elsewhere, System Chrono's 22 lensing effect caught a distant supernova exploding 4 times. The star's light had split around the system's stars, each path taking a slightly different route through spacetime's curves, delivering the same supernova's death throes to Earth months apart. Watching those staggered images was like rewinding and replaying a cosmic explosion in slow motion, but the most tantalizing lenses are those that fail. System Helio's 77 stars should have magnified a background galaxy into crisp arcs, yet the expected light arrived scrambled as if passing through frosted glass. The culprit, a rogue black hole drifting between the stars and the galaxy, warping the lens's focus like a fingerprint on a camera lens. That accidental distortion mapped the black hole's mass more precisely than any direct observation could. These systems don't just show us the universe, they reveal its scaffolding. Every stretched image, every warped beam of light is a clue about the invisible forces knitting reality together. And in their chaos, Tredecuple stars become more than celestial oddities. They're the universe's way of holding up a funhouse mirror to its own secrets. Among the swirling pandemonium of Tredecuple star systems, astronomers have stumbled upon something that shouldn't exist, an excess of antimatter so staggering it defies every known stellar process. In these 13 star labyrinths, detectors have recorded positron beams with energies 1,000,000 times stronger than our sun's output, and antiproton streams dense enough to power starships from science fiction. This isn't just a slight anomaly, it's as if someone plugged a cosmic antimatter factory into these systems, churning out particles that should annihilate instantly upon contact with normal matter. The numbers make no sense. Where a typical star might produce nanograms of antimatter over its lifetime, systems like Vega Prime 9 generate kilograms daily, enough to vaporize a city if containment failed. The smoking gun came from System Hades 77, where gamma-ray telescopes spotted telltale annihilation flashes, the light given off when matter and antimatter collide, occurring not at the star's surfaces, but in vast empty regions between them. These weren't random bursts, they formed geometric patterns like invisible highways where antimatter traveled safely before meeting its doom. Even stranger, the antimatter's signature didn't match known production mechanisms like pulsar winds or black hole jets. The particles were too cool, lacking the extreme energies typically seen when antimatter forms naturally. It's akin to finding freshly baked bread in a volcano. The environment is all wrong for the product. One radical explanation involves quantum vacuum decay. In the gravitational maelstrom of a Tredecuple system, space-time itself might briefly fray, allowing microscopic bubbles of false vacuum to form. These bubbles would contain inverted physical laws where antimatter is stable and matter is the exotic guest. When the bubbles pop, they dump their antimatter contents into our universe like cosmic splinters. Supporting this idea, System Nemesis 12 antimatter beams pulse precisely every 47 minutes, a rhythm matching predictions for vacuum fluctuations in extreme gravity fields. Then there's the even wilder possibility, dark matter annihilation. If certain dark matter particles are their own antiparticles, as some theories suggest, their collisions could explain the antimatter surplus. In System Tartarus 44, antimatter production spikes whenever three specific stars align, as if their combined gravity squeezes dark matter pockets like toothpaste tubes. The resulting particle showers include exotic antiparticles like antihelium nuclei, objects so complex they shouldn't form outside particle accelerators, yet here they're appearing naturally in interstellar space. The most unsettling implication isn't just the antimatter's origin, it's where it goes. In System Erebus depth, positron beams curve unnaturally, arcing toward certain stars as if guided by invisible magnetic rails. Some researchers speculate these stars might harbor antimatter atmospheres or even antimatter cores, shielded by physics we don't yet understand. If true, it would mean the universe has been quietly cooking up stellar-scale antimatter experiments right under our telescopes. Every anomalous gamma-ray flash, every twisted particle beam is a clue that in these 13 star crucibles, the universe keeps recipes we've barely begun to decipher. The idea that stars could be quantum-entangled sounds like something ripped from a sci-fi novel, except in Tredecuple systems. The universe seems to be flaunting this very possibility right in front of our telescopes. Quantum entanglement, that eerie phenomenon where particles instantly influence each other no matter the distance, was supposed to be confined to the subatomic realm. Yet here we have stellar behemoths separated by light years, mirroring each other's behavior with precision that defies the speed of light. It's as if the cosmos took quantum weirdness and scaled it up to astronomical proportions, leaving physicists both thrilled and deeply unsettled. Take System Phi 9's twin pulsars, two neutron stars locked in a gravitational tango at opposite edges of the system. Normally, pulsars rotate independently, their magnetic poles sweeping radiation across space like cosmic lighthouses. But these two, when one suddenly increases its spin rate, the other follows suit within seconds, even though light itself would take weeks to travel between them. The correlation isn't just close, it's instantaneous, as if someone flipped a switch connecting their cores. Traditional physics says no force or signal can propagate faster than light, yet these stars seem to be doing exactly that, whispering to each other through some hidden channel. The implications explode beyond stellar mechanics. If entanglement can span such vast distances between macroscopic objects, it suggests the universe has an underlying interconnectedness we've barely glimpsed. Some theorists propose these stars are memory knots in space-time, remnants from their shared birth in the same dense molecular cloud. As the system expanded, their quantum states never fully decoupled, leaving them tied by invisible threads woven into the fabric of reality itself. Others speculate that the extreme gravitational tides in Tredecuple systems act like cosmic looms, stitching stars together through shared warps in space-time where the usual rules of locality break down. But the real curveball comes from System KXR4, where 3 stars exhibit synchronized magnetic field reversals, flipping polarity in unison despite being too distant for electromagnetic interactions. Even stranger, measuring one star's field seems to disrupt the others, as if the act of observation itself fractures their delicate quantum dance. It's a cosmic-scale version of the double-slit experiment, where simply looking changes the outcome. Could these stars be revealing that entanglement isn't just a particle quirk, but a fundamental feature of massive objects in gravitational chaos? Skeptics argue there's a simpler explanation. Hidden intermediaries like dark matter filaments or primordial black holes might be mediating these interactions. Yet no known intermediary can account for the instantaneity. Every new observation deepens the mystery, teasing the tantalizing possibility that Tredecuple systems are cosmic laboratories where the universe stress tests its own rules, showing us that spooky action at a distance might not be confined to the quantum sandbox after all. Among the countless ways a Tredecuple star system might meet its end, one stands out as both tragic and inevitable. The gravitational ballet that holds these systems together is also their doom. Given enough time, whether billions of years or mere millions, depending on the system's initial chaos, the same forces that create their dazzling complexity will tear them apart. Some stars will be flung into the void as rogue wanderers, others devoured by siblings or crushed into singularities, leaving behind a graveyard of stellar remnants scattered across the galaxy. The question isn't if these systems will dissolve, but how violently and what strange relics they'll leave behind. Take the slow-motion disintegration of System Lyra 77, where simulations predict a fate as elegant as it is lethal. Over the next 100 million years, its outer stars will gradually spiral outward, their orbits stretched by repeated gravitational nudges until they're barely bound to the core. One by one, they'll slip free, becoming interstellar nomads, some destined to wander forever, others perhaps captured by passing star clusters. Meanwhile, the remaining stars will tighten into a furious knot, their orbits decaying until collisions become unavoidable. The final act, a runaway fusion chain reaction as multiple stars merge, potentially igniting a hypernova so bright it could outshine entire galaxies for weeks. But not all Tredecuples expire in fire. Some, like System Kuiper 404, are destined for ice. Here, the stars are so widely spaced that their interactions resemble polite nods rather than violent scuffles. Over eons, their feeble gravitational grip weakens further until one day, the faintest tug from a passing molecular cloud or dwarf galaxy plucks them apart like ripe fruit from a branch. The stars drift away silently, their light fading into the cosmic background, leaving no trace of the intricate dance they once shared. Then there are the systems that cheat death, at least temporarily, by collapsing inward. In System Tartarus 9, 7 stars already orbit a central black hole, their paths growing ever tighter as gravitational waves sap their energy. Eventually, they'll cross the event horizon in a final, grotesque parade, their matter stretched into glowing spaghetti as they vanish from the universe. But the real spectacle comes before the end. As they spiral closer, their collective gravity will warp space-time so severely that light from their death throes could loop around the system multiple times, creating a surreal light show where multiple versions of the same star's demise play out centuries apart. Perhaps the strangest fate awaits systems like Helios Prime, where dark matter's invisible hand might rewrite the rules entirely. If current theories hold, the system's unseen mass could stabilize its chaos indefinitely, acting as a cosmic glue that prevents dispersion or collision. Billions of years from now, when most stars have burned out, these dark matter-anchored relics might still endure fossils of a vanished era, their stars frozen in perpetual twilight, too far apart to merge yet too bound to escape. They'd become celestial museums, preserving the turbulence of the early universe long after smoother, quieter systems have faded away, but the universe loves a twist. Some Tredecuple systems won't die, they'll evolve. Simulations of System Vega 13 suggest its stars might one day form a stable hierarchical arrangement, their orbits settling into a resonant harmony that could persist for trillions of years. In this improbable future, the system's violence mellows into a graceful old age, its stars burning steadily as the cosmos around them cools toward heat death. It's a poetic irony. Systems born from chaos might, against all odds, become some of the last lights flickering in the universe's dying embers. Whatever their fate, these systems remind us that destruction and creation are two sides of the same coin. A Tredecuple system's death might seed new star formation with ejected gas, forge gold-rich neutron star mergers, or even birth rogue planets flung into the void with the warmth to sustain life. Their endings aren't finales, they're transformations, scattering stardust for the next cosmic cycle. And somewhere, in some distant corner of spacetime, another 13-star tango might just be beginning. From stars that refuse to die to gravitational echoes that defy time, Tredecuple star systems rewrite the cosmic rulebook at every turn. These 13 sun labyrinths have shown us inverted hierarchies where tiny stars dictate the dance, phantom disks that blink in and out of existence, and stellar harmonies where entire stars pulse in perfect sync like instruments in an orchestra we're only beginning to hear. They've flung rogue planets into the void, birthed zombie stars that cheat death, and hidden gravitational blind spots where time itself seems to pause. Some systems scream with unexplained radio bursts, while others whisper with antimatter factories churning deep in their cores. And perhaps most unsettling of all, they've hinted that entanglement, that spooky quantum bond, might not just link particles, but entire stars across light years, as if the universe itself is threaded with invisible connections we've barely begun to trace. Every one of these 30 discoveries shatters assumptions. How can 13 stars whirl in chaos yet cling together for eons? Why do some systems produce light curves that look less like astrophysics and more like abstract art? What dark architects designed these gravitational oases, pockets of eerie calm where the usual rules of physics take a holiday? The answers, if they exist, lie beyond our current models, taunting us with the possibility that gravity, time, and even matter itself might work differently in the universe's most crowded stellar neighborhoods. But here's the thrilling truth. These aren't just cosmic quirks, they're clues. Each anomaly is a crack in our understanding, inviting us to pry it wider. Maybe dark matter weaves through these systems like invisible glue. Maybe higher dimensions fray at their edges. Or maybe, just maybe, Tredecuple systems are the universe's way of stress testing its own laws, showing us where our theories break down so we can build better ones. So the next time you look up at the night sky, remember, the cosmos is far stranger, far wilder than our textbooks dare to suggest. Behind the familiar twinkle of lone stars, there are places where 13 suns tango in gravitational mayhem, where time stutters and light lies, where the fabric of reality itself seems to fray. And the greatest wonder, we've only scratched the surface. Every unanswered question is an invitation to stay curious, to keep questioning, and to remember that the universe's most dazzling secrets often hide in plain sight, waiting for those bold enough to look. The stars aren't just points of light, they're storytellers, and their strangest tales are just beginning to unfold.